This is a toolkit lecture. I'm presenting numerical methods of solving both stellar dynamics and hydrodynamic problems. I'm not talking about applications at all. Now, if any of you work using these various simulation tools, you'll know much more about it than I do, but I suspect the majority of this audience probably doesn't work in this area, but really needs a sort of nodding acquaintance with the kind of terminology that theorists use when describing their simulations. And in particular, there's a lot of folklore out there about what you can trust and what you shouldn't trust in terms of, oh, this simulation was done with SPH, don't trust it, that kind of thing. And I'd like to actually sort of get into a little bit more detail about equipping you really to take just a more critical look and know what are the issues for the kinds of problems we have to solve in cluster formation, which kind of codes are good to use. A happy bottom line, actually, on the matter of comparison of hydro codes for use in these simulations is that although a few years ago there was an enormous amount of heat and light generated as a sort of transatlantic battle, SPH versus AMR, adaptive mesh refinement codes, that has really calmed down as both groups are doing the same calculations and getting the same results. And it's a much more healthy situation, A, that you've got two different groups who can cross-check each other's simulations, but also the fact that you can move on from the name-calling about my code's better than yours to getting on to studying the physics. And the physics is actually very interesting, and both groups are producing really interesting subject in this area. We've already heard about the physics of stars only. I will be adding in a number of complications, gas dynamics and magnetic fields, and just reviewing how you might solve these problems. So I've written down the collisionless Boltzmann equation here. It's one way of looking at stellar dynamical problems as being essentially a fluid type problem. You've got stars which are moving in a six-dimensional phase space of real space and velocity space. And if you neglected the close encounters, which Bob described in some detail in the last lecture, the right-hand side of this equation would be 0, and your density of your mass points in phase space would be incompressible in that six-dimensional phase space. But if you want to also add in the fact that stars are not only responding to the smooth potential of the cluster in which they live, but are also having their energies perturbed by encounters, you add in a diffusive term, which is what's being done on the right-hand side of that equation. So early on in the history of this subject, there were Monte Carlo codes developed to solve the collisionless Boltzmann equation. Basically, you're sampling stellar orbits, integrating them, and then periodically applying perturbations which correspond to these diffusive terms corresponding to encounters. And although it's got a long history, I think the main code which is in operation nowadays, and which I will be discussing for one of my results in one of the future lectures, is that by Freytag and Bentz about a decade ago. You can immediately see, and this comes back to Bob and his timescales, that it's not going to be a very good approach to split the problem into a smooth part and a diffusive part if the timescales for those two processes are very similar one to the other. So it's definitely not a good approach for looking at small n systems. It generally finds its greatest utility in solving large n systems like globular clusters. So the much more obvious thing that you do, if you didn't know anything about the subject, would be instead to forget about phase space, put down particles in real space, give them velocities, and then integrate their motions based on their mutual gravitational attraction. Very simple conceptually, and there's a long history of work in this area. Sver-Arsev, who's my next door neighbour in the Institute of Astronomy in Cambridge, was brought over to England by Fred Hoyle in the 1950s. He thought it would be a good idea that somebody should solve these, use a computer and then solve some of these stellar dynamical problems. He's now in his late 70s and is still developing new versions of his Nbody code. So there's a very long pedigree there, and rival codes such as the Starlab code of Simon Potocki-Svart. So nice reviews are contained in books by Sver-Arsev and a lovely book by Heggie and Hutt. Now, there are two things you've got to do when you're solving an Nbody problem. First of all, you've got to determine the potential, essentially the force experienced by each particle, and then you've got to integrate the orbits. Conceptually, that's simple. The trouble is, if you do the most obvious thing you'd think to do of calculating the forces, you do n-squared operations between all the different stars in the cluster, and that obviously becomes computationally prohibitive as you go to large n. So the cunning way around this, first proposed by Barnes and Hutt, was to develop tree code gravity. Is my pointer Have I lost my pointer?
There it is.
No, that's my pen.
That was your first pointer.
It was. I've never had a pointer. Oh, thank you very much. Yeah, okay. Yeah. So sorry, this is a bit washed out, but it's just saying that rather than computing the n-squared interactions between all the particles in the system directly, you clump them in a so-called tree structure, and you make the decision as to whether you open the tree, what's called the node of the tree, which is a clump of particles, and calculate the individual interactions based on the solid angle that that node subtends from the particle you're looking at. So basically what that means is that if things are far away, you group them in terms of their force on the particle of interest, and if they're close by, you look at the individual encounters. And this is an example, very nice recent review by Dane and Reed of Nbody techniques, just showing that in a sort of typical implementation of tree gravity, that if you were doing it directly for this particular system, you'd have about 5,000 interactions, and you've cut it down here by about a factor 5 by doing this lumping of particles at large distances. And the great thing is that rather than scaling as n squares, it goes as n log n, so it's much more forgiving of going to large systems. There's a problem of close encounters, and we've already seen from the movies that Bob showed that close encounters are something we have to model down in the core of clusters in order to be able to understand secular evolution of clusters. And I think this is where I try another attempt at writing on something. So imagine you've got a very eccentric orbit, and I write the potential energy there. It could be a two-body system if we like, just to make it simple, and the kinetic energy here, okay, and the total energy here is constant, of course. Now, if it's a very eccentric orbit, you go in at pericenter, the magnitudes of both your kinetic and your potential energy terms are huge compared with the value of your total energy. So a small fractional error in your, say, kinetic energy when you're close to pericenter can translate into an absolute energy error, which is large compared with this total energy that this has. And so you can easily end up, for example, unbinding something which should be bound as a result of energy errors accrued at pericenter. So you have to be very careful about the integration of eccentric systems when they come close together. Now, being careful in the context of an n-body integration means taking a very small time step. And you can imagine that the time step criterion is going to be roughly related to the local circular orbit time at the radius that you're at. And if you're down at small radii, that's very small. So it's a double whammy. If you really want to be able to integrate these systems accurately, you have to make sure the energy is conserved to a very high order in percentage terms in order to avoid this problem. And in order to do that, you have to take a very small fraction of the local dynamical time, but the local dynamical time is itself tiny. So you want to avoid that, maybe. You don't want to avoid it, of course, if it's the thing that's actually driving the cluster evolution. So this is actually something that we have to bear in mind as we go on. When are we happy to dispense with knowing the details of these close interactions, and when are we happy to, or when do we actually need to go in and study them with high accuracy? But if you are happy to dispense with the details, then you soften the gravitational potential. So all that's meaning is that you add an extra term so that when your separation gets smaller than some value, then your potential becomes constant, and therefore you're suppressing the gravitational force at small separations. So you therefore prevent particles from moving much inside this softening parameter radius here. But of course, although it's a computation expedient, you can't say anything about the things on scales smaller than that. Another thing which I won't attempt to explain because I've no idea how it works, and I think probably these two people are the only people in the world who know how it works, although maybe we have people in this room who know how it works. KS regularization, I can't even pronounce the K and the S, that it's not Kolmogorov-Smirnov, it's something much more unpronounceable than that. But basically it's a way of transforming your equations of motion for gravitational dynamics in such a way that you avoid the coordinate singularity when objects get close together, and therefore you can integrate in a sort of well-behaved manner really close to the, for really close encounters. And basically what happens in codes like Sverre says, Nbody Saas-Fee code. It's a regularized code, and that means that when particles get too close together, you switch from the sort of normal integration scheme to using these KS variables, and you keep that on until they've moved out of a certain tolerance area, and then you return them to the other integration scheme. So that's all built in, and as I say, Arthur's book will tell you all about it. Now, we need to do hydro because we know that our clusters are embedded when they're born. Conceptually, you know that there are two ways of formulating the fluid dynamical equations: Eulerian, where you solve for properties on a grid, or Lagrangian, where you follow individual parcels of fluid and then compute changes in their properties. Quite a lot of what I'll be showing you will be with SPH, so I'll go into a little bit more detail about this SPH method, which is a Lagrangian code, of course. But as I say, more recently, AMR codes have developed terrifically, and later on I'll be indiscriminately showing results from both. The problem with doing Lagrangian hydro is you've got terms in the momentum equation like this, 1 upon rho grad P. So you have to know what your density is locally. And the simplest thing you might do if you have a system of discrete particles is for every particle have a little sampling box that sits on that particle, and as it moves around you count up how many other particles are in that sampling box, divide by the volume, and that gives you the density. And really, in some ways, that's what SPH actually does, except that if you did that, then every time a particle entered or left that little sampling box, you'd get noise. And you really don't want noise, because you can imagine if you've got noisy estimates of pressure and density, you're going to produce jitter in these equations. So instead, rather than just having a sampling volume box which is hard-edged and uniformly weighted across it, you introduce what's called the smoothing kernel. But that's all the SPH smoothing kernel is. It's a way of sampling the environment that every particle lives in and deciding, making an estimate of the density. So it can be written like this: a density which is a weighted average over the masses of the particles. Usually the particles are all the same mass, and this kernel function. This is a very important thing, because from time to time I will just make references to the SPH smoothing length. It is the distance over which you sample particles in order to make this estimate. But it's adaptive in almost all modern SPH codes, so it's always adjusted so you keep a fixed number of neighbours, and therefore your smoothing length is, of course, therefore smaller in regions of high density. The gravity is often handled by the tree. We talked about the tree a moment ago. So your gravity is going to have errors associated both with the lumping together of particles at large distance, but more especially, usually, or in fact all current SPH realizations at the moment, gravity is softened, and it's conventional to set the softening length for the gravitational force equal to the SPH smoothing length for the hydro. So in other words, you start to disbelieve your calculation down at the same scales, both with respect to the stellar dynamics and the gas dynamics, which is a sensible thing to do. There's no point in having one done much more accurately than the other. Now, you've got to have viscosity, because if you didn't, you could have two particles that would just pass through one another if they approach supersonically. If they're going too fast for pressure disturbances to affect one another, they won't know about each other unless you put in a viscous term. So this is done in, say, this way, by early paper by Joe Monaghan and Gingold. Important thing to notice is that the way it's been implemented is that it's symmetric for a pair of particles, and therefore, even though your viscosity may be doing horrible things in your simulation, may or may not be doing horrible things in your simulation, because of this symmetry and because it acts along the vector between the two particles, you always conserve linear and angular momentum exactly, globally for the system. You might be redistributing it incorrectly or correctly, that's another issue, but you've got global conservation built into this implementation. Now, you're not going to be able to digest the way that it's parameterized here, but there's an important point, and that is that there are two kinds of viscosity in a sort of standard SPH implementation. The one that becomes important, there's one that becomes important in the case that the code is detecting supersonic motions between neighbouring particles. So basically, it's this viscosity, the beta term, which is used to handle shocks. And here's an example of a one-dimensional shock tube showing fair agreement with the analytic solution. Now, how does the particle decide on supersonic relative motion? It asks whether the relative velocity within the smoothing length is greater or less than the sound speed. It doesn't actually ask it, but that's something that actually feeds into the calculation of the viscosity. And so I must have a little aside here on disks, as this is going to be terribly important when I tell you about what you can trust and what you can't trust in the simulations coming up. Perhaps I should do the top of the board, might be more visible. Okay, so we have a disk and it's got some Keplerian angular velocity as a function of r, and we've got a particle here, and the resolution is such that it's sampling in its sampling volume over a distance h there. So when it asks what the relative velocity in its smoothing kernel is, the answer is going to be, in the shear flow, about h times omega. Problem with that is that if this is greater than the sound speed, then you'll have this second quadratic term, the beta term, becoming very significant in the simulation. So the problem with this becoming a unpleasantly large term in your simulation of disks cuts in when your smoothing length is large, so that means low resolution. And an easy way to quantify it is, those of you who are into disks, and I don't know how many of you are, will know that roughly the vertical scale height of a disk this way, h, is related to the local Keplerian velocity and the sound speed in this way. So the problem, if h less than h, you're okay, but if h is greater than h, you can see that you've got supersonic motions within your smoothing kernel, and therefore you'll start to get this unpleasantly large term, which is designed to smooth out shocks, but actually there aren't any shocks there. So there have been ways of addressing it. There's something called the Balsara switch, which is in quite common use. What that does is it tries to say that in a pure shear flow, it doesn't impose this velocity, this viscosity term. Problem is that often simulations of star formation are messy. You don't either have a shock, in which case you want the viscosity to be there and to be strong, or a shear flow in which you don't want it to be that strong. You often have material falling into a disk and mixing with the disk, so you've got shocks and shear flows in the same simulation. And I think that is quite a weakness. And the reason why I'm labouring this point a little bit is that when we go on to look at the results of simulations like Matthew Bates' beautiful simulations, the bit I always believe least of all those simulations is how the disk evolves, because there's no doubt that the viscosity associated with the SPH viscosity is far larger than the viscosity that you think physically should be there associated with things like the magnetorotational instability, or people's best guess for the viscosity in real disks. So that is a flag for the kind of problems we'll be looking at here. However, I think SPH has many virtues. It obviously conserves mass because you've got a bunch of particles, and as I said before, the way it's been set up and the symmetries, it's conserving all the global quantities to machine accuracy. In Volker Springel's recent review, he's got a nice statement about the how SPH handles shocks, because you've probably heard, oh, SPH can't handle shocks properly. So what he says, I'll read it out, it's probably not clear from the back. Often the discussion of the numerical accuracy of shocks focuses on the sharpness with which they're represented, and on that basis, SPH has frequently been portrayed as inferior to our Eulerian methods. But it should be noted in both approaches, the numerical shock width is always many orders of magnitude larger than the true width of the physical shock layer. That's actually associated with where real molecular viscosity is actually creating a very narrow region. And so he goes on to say, what is much more relevant than the width is therefore the properties of the post-shock flow are correct, which is the case in SPH. And then he goes on to say that the numerical thickness of the shocks may be reduced arbitrarily by using more particles and is hence entirely a matter of resolution. So, of course, he's one of the great proponents of SPH Springle. He would say that, wouldn't he? But I think that there's a lot of merit in what he's saying, is that there may be some problems where the shock width is particularly important, but that my own view is that that's not the main problem with SPH in these simulations. The main problem, as I see it, is the spurious angular momentum transport associated with the action of the numerical viscosity in disks. And although I'm saying this because we're talking about SPH now, there is also numerical viscosity associated with grid codes, especially as they often difference the disk flow on a Cartesian grid, and that introduces numerical viscosity. So I think both kinds of codes, when they're applied to cluster simulations, the disks are the smallest scale in the problem, and they're not that well resolved, and therefore they probably evolve radially far faster than a real disk would in a real simulation. Now, there's been a lot of talk recently about how badly SPH does with certain fluid instabilities, such as the Kelvin-Helmholtz instability, and there have been a couple of fixes to that suggested by Justin Reed and collaborators and by Dan Price, which seem to work moderately well. I'm not really clear that actually for what we're going to be talking about here, the Kelvin-Helmholtz instability is something we really need to agonize about. So, as I say, I worry about disks rather than the modelling of the instabilities for this. So we want to add more physics. I said yesterday we shouldn't really be throwing away the magnetic field, although we normally do. So when you put in the equations of ideal MHD, you get some extra terms in the momentum equation, and one is an isotropic pressure term, and the other is the magnetic tension term, which is to do with the fact that the field lines want to straighten themselves out. Now, you really want to make sure that you obey Maxwell's equations. You'd think that would be a pretty strong prerequisite, that you keep the divergence of the magnetic field equal to 0. And one way of doing it, if you've done sort of undergraduate physics, is to say, well, if you put the magnetic field equal to the curl of some property, then it will automatically do that. So I'd have thought that was a good thing to do, but Dan Price has a paper saying just don't do that and explaining why. So you can find out why. Another way that automatically conserves divergence-free nature of B is to write it in so-called Euler potentials. So it's writing the magnetic field, which is a vector, as the cross product of two gradients of two different quantities. And the nice thing about this is that when you put that into the induction equation, it implies that these quantities, these scalar quantities, are actually conserved for each particle. So this is really rather simple, because you have your initial conditions, you assign the values of these scalars to each particle in such a way that it reproduces the field that you're wanting to put in, and then you just advect that quantity with each particle. Don't change it for that particle, but at every time step you work out the grad of it and therefore reconstruct the magnetic field. So it's very neat, but it does have some drawbacks, and again, the Price and Bate papers discuss what's involved there. Otherwise, something that's often done is to not set it up in a situation which is going to actually automatically make the B field divergence free, but ever so often clean the system. In other words, diffuse away or remove the divergence from the system. I mean, that sounds to me like an inelegant way of doing it, but again, some people will tell you that it's superior to this. Again, you can read these papers to make up your own mind if you're concerned about this. Now, a very important thing for star formation simulations is the fact that eventually we don't really want to know about the properties of the stars that form, apart from their masses and maybe their angular momentum. We don't want to be modelling detailed stellar structure. So you want to be able to excise the star itself from the domain of detailed computation. Just assign it a mass so it interacts gravitationally with the rest of the computation, but not be modelling it with lots of SPH particles with punishingly short time steps associated with them. So putting in a sinc particle in SPH is very easy because it's a Lagrangian code. So what you do is you have a criterion. You first of all in your code you assign a sinc radius. So that's done by the user. And obviously you set a large sinc radius for computational economy and a small sinc radius if you really want to be able to resolve things down to small scales. And The simulations I'll talk about use a variety. So you should use some simulations for, say, looking at large-scale clustering, and others for looking at the details of the binaries because they use different sink radii. And then having defined what the radius of this sink is, you just have a criterion that any particle that falls within this radius, if it's bound and gravitationally bound and doesn't have enough angular momentum to have a circular orbit at that radius, then you say it joins the sink. I should, just backtracking a moment, you create the sink by having a requirement on having bound material above a certain density within that radius. So at that point, you replace your SPH particles by your sink particle, but this is the criterion for deciding whether something else that strays within our sink should be added to the particle or not. And again, it works very well, except there's an issue with disks. So going back to the whiteboard, so here's your star, here's our sink. Now usually for any annulus in the disks, it's being torqued down, T-O-R, torqued, yeah. Right. It's being slowed down by the material that's going slower than it on the outside and sped up by the material on the inside. And it's a slightly balance between the two that drives your material in the viscous disk. But supposing you now say, well, I'm not going to have any material in there because I put it all on the sink. You don't get any of that spin-up torque for this. That isn't there for this inner annulus, and therefore it's only got spin-down torque, so it artificially accelerates into the sink. Now it goes to the next annulus out, it's the same problem. And so you actually eat away at the inside of disks. So you really expect your disks to be depleted in mass within a factor of several of the sink radius. And what that factor is, of course, depends how long you run your simulation for, and also what your artificial viscosity and what your code is like. But there is a caveat there.
Cathie, why is this necessarily an issue only for disks? Why not for a bigger cluster, big molecular cloud simulations where you also turn a star into a sink particle?
Well, they're usually pretty centrifugally supported by the sink radius anyway, but certainly if something's falling supersonically into a sink, which it is, there's no way of communicating the fact that there's nothing there ahead of it. So actually that's the reason that in a shear flow it's falling in very subsonically, and it knows about what's inside itself, whereas if you're just posting stuff down radially, it doesn't care. But in most simulations, your sink radii are sufficiently small that actually you do get a disk down there, so it is relevant. So actually in Matthew Bates' thesis, he did experiment with putting clever sinks in. This is my idea for his thesis, in fact, was that you would have not just empty stuff there, but you'd put in pressure forces and torques there so that you didn't get this effect. But it never really worked that well, so I don't think he ever published it, and he's abandoned it. But maybe there's work to be done there. Okay, modelling thermal physics with SPH. Again, this isn't actually SPH specific. This is what you have to do. You have to relate your pressure to your density in order to be able to calculate the acceleration terms. So you can solve the thermal equation. You can look at the balance of heating and cooling, or much simpler, and what's been done in the majority of simulations in this area up until a couple of years ago, is instead to parameterize the equation of state simply as a barotropic relation. And the simplest thing you can think of is making it isothermal when it's low density, and then when it gets high enough density, you make it adiabatic. So you have a dependence of rho going as the 7/5 power, which is appropriate to diatomic gas. I do put adiabatic in inverted commas there as just a little sort of note for the purists. It's not really adiabatic because an adiabatic system, when it goes through a shock, this coefficient out here should change. You should generate entropy in a shock. If you keep this constant, which is what is done in these codes, then you don't generate any entropy in the shock. You still have the material sitting on the same adiabat when it's gone through the shock. There's actually been a recent paper, again by Matthew Bates, comparing these calculations with full radiative transfer, And actually, this effect is not a massive problem. I thought it might have been more of a problem than it's turned out to be, but it's just a little thing to bear in mind. And where do these numbers come from? And why do we decide to make it isothermal and adiabatic? Well, it's because in spherical symmetry, you've got the luxury of actually doing the radiative transfer properly, and old references to Richard Larson, but more recently to Masunaga and Inutsuka. They calculated the collapse of a spherical cloud, and in the process were able to derive the sort of mean pressure density relationship from that, and then that is then plugged into the SPH calculations. But of course the SPH calculations are not for spherical situations, so there is a big leap going from one to the other, which is why you really want to get beyond merely parameterizing in a barotropic fashion how to get from density to pressure. But it'll be quite important for the discussions, where does the universality of the IMF come from? Neil mentioned it this morning. There are some subtleties of what you can do with this barotropic equation of state, which can be quite important with imprinting the IMF. So we'll come back to that later. Yeah.
If you try to simulate a core collapse, if you start with a small density,
Yeah.
so you start with isothermal, and then
Yes.
at some point you will have to switch to adiabatic.
Yeah.
And does this introduce any discontinuity or problem in the code? Or
No, because it's done.
It's
It's not. No, it doesn't actually. It's you do it smoothly, basically. So obviously, if you had a discontinuity in the pressure where you went from one to the other, that would be a problem. But as long as the pressure is a continuous function of the density, then that's okay in practice. Now, putting in the thermal physics, you don't have to digest what's in here. It's just saying that there's a modification of the, well, there's actually U is not velocity, it's actually thermal energy. So it's saying if we don't prescribe the relationship between pressure and density, we actually have to solve for the energy per unit mass of every particle. And that in addition to PDV work, you've got the energy that it's exchanging with the radiation field. And then you have another equation for solving the evolution of the radiative energy locally. Now, the nice fix to that problem is something called flux-limited diffusion. And basically, it's a parameterization of this equation. I haven't actually written up here that the evolution of the thermal density goes as the divergence of the flux. So there should have been an extra little bullet point there. So we need to know what the radiative flux is locally, and then if we can work out its divergence, we can work out the cooling. And how do we prescribe the radiative flux locally? Well, you know from studies of stellar structure that if it's very optically thick, radiation is diffusing out, and therefore the radiative diffusion approximation is appropriate. And this flux-limited diffusion is just a mathematical fix that is saying as long as you're at large optical depths in your structure, then you use something which tends to the classic radiative diffusion approximation. If you get to low optical depths, that actually diverges. You've got this 1 upon kappa on the bottom, so you're down in regions of very low opacity locally, your flux would blow up, and that's because you're actually applying the diffusion approximation out in a regime where your photon mean free path is long compared with the length scales of the system. So to solve that, you switch to simply advecting the radiative energy at the speed of light beyond when you get into the optically thin regime. And so we've got a mathematical parameterization for how to work out the flux in these two limits, and it goes smoothly between the two, work out the divergence of that, and you've got your heating and cooling. So it's quite tricky because you have to work out a divergence of something which also involves a gradient, and that can be noisy in SPH. But a series of papers by Whitehouse and Bate which set out how this can be done. Computationally expensive though, you have to actually integrate the equations implicitly because of the very short timescales associated with these equations. But let me just do a little caveat on flux-limited diffusion because, as I say, everybody uses it. Well, I think everybody in this field almost uses it. Putting in the flux limiter is a good way of providing a boundary condition at the outer edge of your calculation. Say if you've got a collapsing core and it's optically thick in the middle and then it gets optically thin at the outside. So it's good for that. What it's not good is for actually getting something believable for the temperature structure in that optically thin region. So as long as you don't care about what's happening in detail in the optically thin region, it's fine. But just to give you a simple example, if you merely advect radiative energy at the speed of light, the temperature that you predict at a radius r from a point source just becomes the temperature of a black body grain that you put at that temperature. Okay, we know how to calculate the temperature of a brick placed 1 AU from the sun. It's exactly that calculation. So that's the temperature structure that flux-limited diffusion gives you when you've got optically thin material. And this is just a recent calculation by James Owen showing that whereas this is what you get applying flux-limited diffusion, and these temperatures here are about 400 Kelvin, this is in the optically thin regime, if you do a proper Monte Carlo radiative transfer calculation, which takes into account the fact that your grains are really small and are not radiating efficiently as black bodies, it's way hotter. I mean, it's up like sort of 1800 degrees. I mean, this is an enormous difference. So a lot of calculations in the literature, including some of the nice calculations done by Krumholtz and collaborators on massive stars, up in the optically thin regime, they're using this approximation. And I think it's fine if you're not interested in the dynamics in the optically thin regime, but if that's really important, then you know there is a beware there. I'm not proposing a solution, by the way, because you don't want to run a Monte Carlo radiative transfer scheme on this because it takes days to process a single screenshot. So another nice way around this was proposed by Dimitris Stamatelis here, and saying that actually you can simplify down these equations to a form of this. So this is a rate of change of the energy per unit mass. And the form of this equation, T0 is just allowing it to equilibrate with some background if you want it to. And these other terms ensure that you recover the radiative diffusion approximation if you're optically thick, and you give the correct answer for emission from an optically thin region in the limit of very low optically depth. And this is a pretty good formula to use, and if you were put it into a grid code, it would be very straightforward, because in a grid code it's easy by just running up your grid to calculate what is the optical depth and what is the column density. We'll come across this a number of times when I talk about putting in feedback, that doing this in SPH is a bit non-trivial. It's expensive. You don't want to be sort of walking out through particle lists and calculating column densities from your particle to infinity. And so you'd really like to have a computationally cheap way of getting around this. And Stamatelis et al. Suggested that if you just use the density and potential locally, which is actually stored by each particle in the code, then by doing a mapping onto the equivalent relationship between these quantities and the optical depth and column density in a polytropic sphere, you can get an estimate of what the optical depth and column density is. And this does work well in spherical symmetry. It does rather overestimate the column density in disks in a systematic way, but we've come up with a method which, for use in disks, seems to improve on that by using the vertical component of the gravitational acceleration in disks, and that removes the systematics. So I think there are cunning ways around in SPH of not necessarily doing full flux-limited diffusion, but using an equation of the sort I've just shown, and fairly economical ways of estimating those quantities that you need, like the optical depth and the column density. Now that was pretty much all SPH, but let's look at the Eulerian hydrocodes, and they come in the flavours of keeping your grid fixed. And for the calculations that we'll be talking about, you really instead need an adaptive mesh refinement code, an AMR code, because that way you can continually, as your simulation evolves, put the resolution where you need it by creating subgrids. Obviously, SPH does that automatically. SPH is conceptually a lot simpler. It got going in this area first, but AMR is definitely catching up, and for some problems, it's much easier to implement some physical effects in AMR than it is in SPH, and vice versa. So, I think it's a great situation now that we've got two independent methods doing the same problems. One of the things, I've said some of the things that are easier to do in grid codes than SPH codes, like calculating column densities, but something that's harder is putting in a sinc particle. A Lagrangian code lends itself to that very easily. You know, you just say, okay, this is collapsed, put it in a sink. In a AMR code, it's actually quite a tricky business when you've got a particle that's moving with respect to, sorry, not a particle, mustn't think about particles. You've got a flow, you've got a high density region, you don't want to refine and refine and refine and waste all your computational time on that. So you want to replace it by a sink particle. But Krumholtz and collaborators have solved that nicely in 2004. It seems to be working well. They did some nice test problems to demonstrate that it's working well, and now it's routinely in all their calculations. And that's really the technical fix which has allowed AMR to now come up and be competitive and do the same kind of simulations as SPH. Until you could put sink particles in, you couldn't do cluster simulations with AMR. Now you can, so that's good news. And I mentioned at the beginning the sort of period of mudslinging about 10 years ago. None of that ever got into print, interestingly enough. It was all played out in conferences quite colourfully. Finally, the people I think who actually published a proper comparison of an AMR code and SPH code, given the same problems and really test problems applicable to these kinds of cluster formation simulations, and did the proper comparison, was Federath et al., the Heidelberg group. And it's a very nice paper. It's very detailed, but the bottom line is that the agreement is pretty good. And I said that's the great thing, is that we can now move on from the mudslinging to looking at the physics. Now, a few extra things we want to do. If you're looking at torus, we don't have to worry about that, but as soon as you have massive stars, then you've got ionization feedback to consider. And we've heard a little bit about how this may or may not perturb the dynamical states of systems. Now, if your gas is dense, and usually in these kinds of simulations it is dense, and I'll say how dense in a moment, you can use the on-the-spot approximation. You probably know what this is, but it's simply that an ionizing photon comes in and it ionizes an electron from the ground state of hydrogen. So it leaves. And the thing is that if an electron then recombines, if it goes back to the ground state, it will produce another ionizing photon. And so if that happens locally, you haven't actually done anything. Whereas if it recombines to, say, the n equals 2 level, then it hasn't got enough energy to, the photon release hasn't got enough energy to ionize hydrogen. Of course, the energy comes out in a couple of photons, it cascades down, but they're all irrelevant to further ionization. So the on-the-spot approximation says that if it's dense, your medium, then you can forget about the recombinations to the ground state. It's almost as though they didn't happen. You know, the photon went in, booted the electron out, but the electron fell back in and produced another ionizing photon, so we forget about that, and that all happens locally. And therefore, when we look at a balance between the numbers of ionizing photons arriving and the rate of recombinations, we only consider these recombinations to the n equals 2 level, and that's encapsulated in this case B recombination coefficient. So this is just a rate over a volume of the number of recombinations per second. It's got an n squared term in there. Yeah.
What is actually the ratio in which this recombination goes to the NS1 or NS2?
Ooh, gosh, I can't remember off the top of my head. It's if you look at there's an alpha A and alpha B are the two recombination coefficients. So one is the total and the other is just to n equals 2. Does anybody know it off the top of their head? It's it's of order unity. It's not 10 to the minus 5 or something. It's, I don't know, a third or something like that. I don't know. I can find it out. But if you want to know the answer, it's just a ratio of those coefficients gives that. So making sure you use the B coefficient, the classic Strongum criterion for deciding how far your ionizing radiation penetrates is to add up all the recombinations over a sphere and equate that to the number of ionizing photons that are produced per second. And that's for a sphere, but if you're not interested in the diffuse ionizing field produced by these guys, which have been released by recombinations to the ground state, if we say they just get it all absorbed locally, then we can apply this kind of criterion along any line of sight from your source. You're just totting up total number of recombinations and equating it with the total number of ionizations per second. Why we're so interested in doing that is that within that region, the temperature is now about 10 to the 4 K, and beyond that region, it's whatever it was before. It's a very sharp region separating an ionized bubble from cold gas beyond that. So again, this is an example where grid codes come into their own, because it's pretty easy to calculate an integral of this sort if you know where your material is on a grid. Not so easy in SPH, but Jim Dale in his thesis a few years ago, and also some earlier work by Kessel, Daynard and Burkett, managed to find a pretty good implementation in SPH for doing these integrals in a time-efficient way. And more recently, the results of doing that, this is a simulation of a cluster forming where you've got an ionizing star down in the center. This is using the Dale ionization algorithm showing you which parts of the cloud this algorithm thinks should be ionized. This is comparing it with the Moccasin Monte Carlo radiative transfer code, thanks. And the agreement is pretty good. The point is that this doesn't make the on-the-spot approximation. This allows the ionizing photons to propagate. And there's another way of doing it, which is in using cosmological simulations. So if you're interested, there's the Petkover and Springle reference there. I want to add myself. Oh yes, I'm fine. Right, good. So the other extra effect you might want to put in are stellar winds. Again, easier to do in grid-based codes than in SPH. In fact, the best implementation in SPH, or possibly the only one I know about, is work by Dale and Burnell, where they have to spray out at periodically in their code, they spray out virtual particles. These particles don't actually carry any momentum. They come out from the source, and they're used just to explore what's the environment around the source in terms of SPH particles. And they're used to calculate, therefore, how much momentum should be given and to which particle on that time step. They are then not used. You don't introduce any extra particles into the simulation. They are just introduced for a moment to figure out where the momentum goes. Then you add momentum to the particles and allow it to go. Again, it's easy to get a code like that to reproduce similarity solutions in spherical geometry. One of the big problems always with these kinds of calculations is that the test problems are always in toy geometry. They have to have analytic solutions, and it's relatively easy to get them to work. And then you go off and apply it to a completely different situation where there aren't any analytic solutions, and you hope that it works just as well. And that's just a general thing. Now, looking to the future, you may have heard of a Repo. This is Volker Springel's new sort of SPH-like beast, because it's an interesting sort of hybrid between the Lagrangian and the Eulerian. It solves the fluid occasions on a moving Voronoi mesh. So this is viewed somewhat in Springle 2010, and there's a series of papers by Debris Sajaki which just looks at a Repo versus conventional SPH, and they're particularly looking at it for cosmological simulations, and therefore they're testing it on problems which are very important for cosmologists, such as when you have halo substructure falling in through protogalactic disks and whether the integrity of those clumps and lumps is preserved. And they find the superiority of a Repo relative to conventional SPH. So all the cosmologists are now saying, oh, we can't use SPH, we've got to use a Repo. Unfortunately, it's only Springel and Hernquist and their collaborators who've got a Repo. It's a private code. But I don't think this should sort of spread necessarily too much wide panic in the community, because cosmological simulations have always been far worse resolved than simulations in this field, just for the obvious reasons they're trying to capture a much larger range of scales. And whether we'll have an opportunity to test this code on star cluster applications, that really depends on the politics, I guess. But it's not necessarily all good news, because, as I stressed earlier, conventional SPH conserves certain quantities like the angular momentum to machine accuracy, the way it's formulated. This new method doesn't. So again, how is it going to behave in disks? don't know, but just pointing out that it's out there. Now, I said earlier that you always have a compromise, that you want to be able to model the stellar dynamics accurately, and I said how computationally complicated that is for doing close interactions and pure Nbody systems and using this KS regularization. But you also want to be able to do that in a situation where you've still got gas. And SPH calculations use smooth gravity, so they're not good for looking at detailed interactions on small scales of the stellar dynamical systems. And so there's 2 ongoing code developments at the moment that I'm aware of, one by David Hubber and one by Nick Mokel, who are trying to improve on this situation. In other words, marry together the best bits of SPH and stellar dynamics, improve the integrators that are used for following the motion of the sync particles so that you could actually model close interactions in stellar systems, but still have the gas there, because normally what happens in calculations where somebody says, I'm going to do a stellar dynamic calculation and put in a gas potential, it's exactly that. It's just a prescribed rigid potential in which the stars are moving. It's nothing like what's happening in a real cluster formation simulation. So you want good stellar dynamics, and yet you want the stars still to know about the gas, and that's an important one. And in the same spirit, there's this AMUSE venture, Astrophysical multipurpose software environment, and this is the brainchild of Simon Portuguese-Svart in Leiden. And his idea is that there are all sorts of public codes that are out there for doing all sorts of problems like hydro and stellar evolution and Nbody, and that if you can create a sort of user-friendly script that can interconvert the variables from the parameters from all these different codes and allow them to work in tandem with one another, this would be an enormous facility for the community. Obviously, the results are only going to be as good as the component codes are good, and they've been tested by their creators over the years, but the idea is that we now got to the point where you need some sort of overarching structure in which users can actually summon within one simple script one code to do the hydro and one code to do the Nbody dynamics. Very interesting, and of course in the same spirit as what I've just mentioned about the Hubber and Mokel efforts in this area. But I think it's just a case of watch this space on that one. So I'm done. Yes.
Besides acting as a viscosity source,
Yeah.
what else does the gas do that's interesting in terms of stellar dynamics?
Well, it provides lots of the potential, actually. I mean, viscosity is something which causes the gas to evolve radially in the disks, but it doesn't have any effect on the stars. So the main interaction with the stars is both gravitational and the fact that it's accreting onto the stars during the simulation. So you have to be able to model both of those. Yeah.
As far as I know, the first stars community of zero metallicity has access to a repo, and I think Clarke possibly has done one of these first cluster simulations.
That was with a Repo, was it?
Yeah, I think so, yeah.
Was it? Oh, okay, right. That's interesting. Yeah.
So, it might be...
Did he do a comparison with?
Well, so this is the problem. I didn't read the paper, so I was actually going to ask you.
Well, I thought that's first stars. Nobody will ask you about first stars at this meeting. Interesting, though. Yeah.
Okay.
Yeah.
I'll just
Yeah.
look at that.
Yeah. Yeah.
I may talk about this in one of your later lectures.
Yeah.
There's a paper that Matthew wrote in 2009 where he reproduced the binary statistics of the field incredibly well.
Yeah, that's right. Yeah.
Some of the matches he got were obtained when he changed the sync particle radius.
Mm-hmm.
So that changed both the eccentricity to a lower eccentricity value, and I may be wrong in saying that he could change the separation of the seven major axes as well. So I just wondering.
Yeah. Well, I will. Actually, I think it's lecture 4 or 5. Something starts with saying there's this wonderful simulation and there's a hierarchy of what you should believe in it. And eccentricity is down at the bottom because it's really easily perturbed by interaction with the disk, and I don't think the disks are modelled. Semi-major axis is sort of similar but not as bad because we usually only care about semi-major axis in a logarithmic sense, whereas we know we want to map the eccentricity on a linear scale. So that's a much more delicate problem than the question of where does the mass go on which star. So yeah, I think that is a very important issue. Yeah.
You said that in SPH usually you assume that the smoothing length
Yeah.
is the same as the softening length.
The gravitational softening, that's normally done,
But
yeah.
sometimes people assume that they prefer to fix the number of neighbors instead of fixing the smoothing length. What do you think?
Well,
how does it change?
yes, the normal implementation nowadays is to fix the number of neighbours, so the smoothing length changes, therefore the softening length also changes. Okay, so it's different for every particle, but it's all symmetrised. Is it ski time?
It is.
For some.
Thanks again for our morning lecture. See you all back sore and sunburned at 5 p.m.
Ha.